Chapter 5 is about the fast Fourier transform, which is a topic that's not normally covered by texts on computational linear algebra, but it does have something to do with linear algebra, and it's an interesting topic, so let's do it. You're probably familiar with the Fourier transform, where you expand a continuous function, say y of x, as an infinite series of sine or cosine terms, f sub j sine of j theta, that is y of x would be the summation of f sub j sine of j theta. Well, the discrete version is basically just a discretization of that, except our function is only defined at discrete integer points, and it's expanded as a Fourier series coefficients f sub j, and this can be thought of as basically it's analogous to the sine of j theta. It's a complex function, but it's has frequency j minus 1. So basically the discrete Fourier transform is just a matrix vector multiplication. In other words, the right-hand side here is just the product of a matrix A times a vector F. F represents the frequencies, and A is this matrix here. Well, actually, that's the inverse. A sub kj is this matrix right here. It's complex, so it's basically the multiplication of a n by n matrix by an n vector, which would normally take n square operations, but with the fast Fourier transform, we'll see that it basically takes order n, n log n actually, but that's almost the same as order n operations. So it's just a fast Fourier transform is just a very fast way of multiplying this matrix times this vector. And let's take an example to see what the discrete Fourier transform is useful for. Suppose you have a set of data points. Your y sub k represent the temperatures. Y sub k represents the temperature after k hours, and you record the temperature at a certain weather station for 100 years every k hours. So you have this big set of data, 100 years worth of hourly temperature representations. If you plotted it as a function of k hours, you would probably observe a daily cycle with a period of 24 points. The temperature would vary daily over a cycle, and then you would no doubt observe an annual cycle also, that is every 24 times 365 points. I'm going to show you a plot of such a temperature time plot, although it's actually not this frequency. It doesn't have these two frequencies in it. So your plot of y versus k might look like something like this, where you'd have an annual cycle. This would look like it might be about 4 years worth of data, and then you'd have a daily cycle. Well, as you can see, this isn't really a day and year here. The frequencies are different. We'll see later what this plot is, but you'd have something like this with an annual cycle and a higher frequency daily cycle. But you would like to determine the F's, the coefficients in your Fourier expansion for that data set, and that would tell you a lot more easily what the frequency distribution of your data is. And with the weather temperature plots that I was just talking about, if you were able to calculate your F's using the discrete Fourier transform and plotted F versus frequency, you would have a couple of peaks. You would have one corresponding to a daily cycle and one corresponding to an annual cycle. As I say, this data that I just showed you isn't really time temperature plots. It has different frequencies. It has actually, as you could tell, a plot with frequency 4. In fact, let's go back to that plot This one, as you can see, has a one underlying frequency of 4 per the entire set of data, and another one with a frequency of turns out to be about 18. There's about 18 of these little cycles. So when you plot it, you see clearly the frequency of 4 and the frequency of about 18. And if you actually plotted the temperature plots that I was talking about, determine the frequencies there, you'd see a peak with a frequency of however many days there were in the total data, and another with however many years there were in the total data. You would see that a lot more clearly. So that's the kind of thing that it's useful to get the F's out, given the J's, given the Y's, given the data, plot the frequency. Electrical engineers do this kind of thing all the time. Given a set of data, basically plot the spectrum, see what frequencies are present and what their relative magnitude is. So that's one reason we'd like to do a fast Fourier transform, discrete Fourier transform, to get either from the frequency domain to the time domain. The F is the frequency, F sub j is the frequencies, Y sub j would be the time plots. In the example I was just talking about, we actually want to go the other way, and we want to calculate the F's given the Y's. That's an inverse Fourier transform, but it's almost exactly the same as doing a forward transform, because it turns out that the matrix A inverse, see, Y is simply A times F. If you want to find F given Y, as we do when we want the frequencies given the time, you simply calculate F equals A inverse Y. But it turns out that A inverse looks almost exactly like A, except for a factor of 1 over n and a negative here. So basically, A inverse is just A conjugate over n. So if you can calculate a forward discrete Fourier transform, you can calculate the inverse transform just as easily. Okay, so you can always do either the forward or the inverse transform by simply multiplying this out, multiplying the matrix A times F, or the matrix A inverse times F times Y to get F. But that would normally be order n square work, because matrix vector multiplications order n square work. And some applications, often n is really huge, like the one we just talked about. There would be 100 years worth of data taken every hour, so that's a lot of data. N would be pretty large. The discrete Fourier transform is basically just a way of doing this matrix vector multiplication much faster. And it takes advantage of the fact that the matrix is not just an arbitrary matrix, it has a very special structure. And the details are in the text, but the bottom line is this expansion right here. If you want to multiply your matrix A, your special matrix A times F to get Y, it turns out that to do that, you have to multiply two matrix vector. You have to do two matrix vector multiplications of half the original size. In other words, if A is an n by n discrete Fourier matrix, B is the n over 2 by n over 2 matrix. So of course we're assuming n is even, so that you can break this up and have into two parts. But you see, to do the whole n by n matrix multiplication, you basically have to do two n over 2 by n over 2 transformations, B times F odd and B times F even, or F odd are the odd components of F, F even are the even components. The first half of Y is this, the second half is that, and basically you just have to do two matrix multiplications of size n over 2 by n over 2. And you see, normally to do n by n matrix vector multiplication, you have to do 4. You would have to take this piece of the matrix times that, you'd have to take this piece times that, and this piece times that, this piece times that. There would be 4 matrix multiplications of size n over 2 by n over 2. With the special structure of the Fourier transform matrix, you only have to do 2. So basically, doing an n by n multiplication is only twice as much work as doing an n over 2 by n over 2 multiplication. Therefore, the total amount of work is basically linear. It's proportional to the size. Well, now that's assuming that n is a power of 2, so that you can break each one down into even parts. In other words, to do the n by n multiplication, you can break it down into n over 2 by n over 2 parts. Then to do the n over 2 by n over 2, you have to break it down similarly, recursively, to n over 4 by n over 4. So we're going to assume that n is a power of 2. If it's not, then this doesn't work as well. There are ways much more complicated to make it efficient if it's a power of 3, for example. But basically, if n is a prime number, there's nothing to be gained by the fast Fourier transform. So we're going to assume that n is a power of 2 in order to take full advantage of the fast Fourier transform. Okay, there's a Fortran and a MATLAB program in the book that do the fast Fourier transform recursively, and it's a remarkably simple routine. This is the whole thing essentially here. Notice the key is that to transform a vector of size, vector y of size n, you have to do true transformations of size n over 2, and you take the odd part of f and transform it, and the even part transform it, and then you merge them together, and this is a small amount of work here compared to that, and this is recursive. The routine is calling itself. So you end up, as I said, you're doing an n. Transforming an n vector is only twice as much work as transforming an n over 2 by an n over 2 vector. So the total amount of work is basically proportional to n, not n squared. Here's the set of data that was actually what was in those plots I showed you earlier. You have if you look at y in this form, you can see clearly that y is going to have a component of frequency n over 30. N is n being 128 here. Notice n is a power of 2. So it has this term here has a period 30. This has a period of 7. Therefore, is frequency n over 30. Frequency being the total number of periods during the data. And so this component has a component. The y data has a component of frequency 4.27 and another component of frequency 18.29. That is period 7. And if you plot y itself, you can sort of see the two periods there, the one of frequency 4, 1, 2, 3, 4, a little more than 4, and the one of frequency 18, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, superimposed. In more complicated situations, it won't be nearly as clear to see the spectrum, but you do the inverse transform to get the f's, and you get the figure that I showed you a minute ago, and there it's really clear what components you have there, what the spectrum looks like. You see the frequency peak at 4 and the other one at 18. There's actually also one at 0 for the constant term, frequency 0. And as I said, to get the f's from the y's, you're actually doing an inverse transform, but inverse transform is really easy because A inverse is simply the conjugate of A over n, so you simply take the conjugate of y, do a normal forward transform, divide by n, and then conjugate again, and you've done an inverse transform. Another important application of Fourier transforms, fast Fourier transform, is in the solution of some partial differential equations. And there's a problem in the text where you solve a partial differential equations, this two-dimensional partial differential equation of this form with periodic boundary conditions. And if you use finite differences, you get a set of finite difference equations. The reason the fast Fourier transform is useful is if you expand your f in a Fourier transform and your u in a Fourier transform, your solution u, you can relate the coefficients of alpha and the coefficients of b. And so if you can calculate the coefficients of alpha, and you do that with a inverse transform, then you get the coefficients of u easily. And once you have the coefficients of u, you can find u with a forward transform. So you basically need to do an inverse transform to find the coefficient CLM, and then you immediately get the BLMs, and then you do a forward transform to find u. And as you might expect, all of this can be done very fast. Basically order n square work, and that is extremely fast because normally other methods for solving those finite difference equations are at least order n cubed. In fact, it's easy to see that this is really optimal. You're never going to find a method that's faster than this to solve those equations, because order n square, that's your vectors are order n square here. Your vectors f and u, and just storing them takes order n square work. So this is optimally fast way of solving certain partial differential equations. The catch is that it only works for certain partial differential equations. Have to be in a rectangular region with constant coefficients. For more general PDEs and general regions with variable coefficients and so forth, this method simply won't work. But when it does work, it's the fastest thing around.